this is the equator, and this is the plane for the equator plane. Okay. And then this is what we call the polar orbit. Polar orbit. So, and this polar orbit means that the satellite is revolving. So this is the North Pole, this is the South Pole, this is East, this is West. So the satellite will be revolving from the North Pole to the South Pole. So this is what we call the polar orbit. And this we call the equator. And this we call it the Earth's surface. Earth's surface. And this is North Pole. So this we call the South Pole. The South Pole. And this we call the North Pole. North Pole. Right? So that is how the polar orbit look like in practical spacecraft. Okay, well enough. So that is that we don't discuss too much on these polar satellites, but you're not limited. You can use review physics such as physics books such as Nelcon's, or we call the Principle of Physics by Nelcon's, or Principle of Physics by S. Chandy. Those are the authors. And you can refer also physics books, advanced books for Roger Lancaster. You can learn furthermore from a point where, but according to the syllabus, this is even more than what the syllabus is asking you to learn. Okay, so let us continue with our sessions or lecture or period 60 concerning about the orbit of the artificial satellites. That's what we've been discussing from the beginning of this lecture. And a few minutes ago, I've been teaching about the polar satellites, and then I told that these satellites, they revolve around the Earth in the polar orbit. So before I end these sessions, I would like to tell you the basic applications of this satellite. Why does the Earth need polar satellite? That's the questions. Where do we apply them? So why do we need them? Why the Earth was not satisfied with geostationary satellites? So I would like to answer that question quickly and then leave the homework for you, and then meet you in session 7 after this. So the basic applications, we say that the polar satellites are used to record land and sea temperature. So the polar satellites, right? The polar satellites are used to record. Okay, used it to record. So this is recording what? Record the features and everything about the land, the features, right? The features. So this we call it the features. The features. The features of the land and the sea temperature. The sea temperature. The sea temperature, right? And this is the reason why, in case that you are online, you might know the temperature of the place where you are. You might think that maybe your smartphone or your iPhone has, or your computer or your iPod has a thermometer within it, but it's not true. Because of the applications of the satellites, you might find that we can find even our local information. For example, if you want to go to Mwanza, and then you don't know the direction of the hospital where you want to go, or maybe for instance, Uganda. So you can use the GPS satellites, right? In order to have the right directions to know that where will I go through in order to arrive at that place. So in case of these polar satellites, it helps us to know the features of the lands and the sea temperature. Okay, because you know that the Earth's compositions, it has the land features and also it has the sea features. So now let me leave the homework. So this will be homework 6. Homework 6. Okay, the homework 6 is this one. Explain briefly the concept of 40 of the weightless. Explain briefly the concepts of the weightless. Okay, so we call it the weightless. Weightlessness in the satellite. So this is the homework. Make sure you do it before you join me in period 7 or lecture 7 of gravitational mechanics. So explain the concepts of weightlessness. So this is the keyword, weightlessness in the satellite. What does it mean? What the means of weightlessness in the satellite? Right? So you are the physics students, and actually that you are good enough right now, you are expert in concepts of gravitational, you have to explain what happens when a man or a human being is in a certain satellite, what's going to happen about his weight. So that's all that you have to go through in case of the orbit. I told you about gestationary orbits, I told you about parking orbit, I told you about the free orbit, I told you about the height of the satellites, and etc., etc. I told you about many phenomena just within a short of time. Make sure that you watch this video several times as well as you can. And then you have to make sure that you subscribe onto this YouTube channel that known as Tanzania Online A-Level Secondary Schools, in square bracket Olenjolai 10M. So again, you share this video to your colleagues, to your friends, to your classmates, to your schoolmates, and then insist them also to do the same, because we'll be uploading a number of videos, many videos in this YouTube channels to teach the A-level students of advanced physics. So make sure that you subscribe so you get information or informed in case or at any times when you add a new video onto this channel. Thank you very much. I thank God for giving me this chance. I thank you also for taking your time to watch this entire video from the beginning to the end. In case you have questions, make sure that you use the comment sections in order to ask your questions as well as you can. And if you have any kinds of the comments, please leave it means that you use the comment sections of this video. So thank you very much. See you in the next lecture. Okay, so let us go now to a very interesting point of derivations, because you know physics is just advanced physics mentor students or training students on the concept, explanations, description, derivations, and the main part is solving problems. So in order for us to solve some problems, we need a formula. So now I would like to take you into a very interesting point of derivations of the formula of determining the height of the parking orbit from the Earth's surface. So I've been teaching you about the parking orbit, but let us speak now mathematically. We'll be following some of the steps on achieving it. The first step, we say that consider a satellite. So consider a satellite of mass m. So consider a satellite of mass m revolving the Earth's surface. Revolving the Earth's surface, right? The Earth's surface at the height. So at the height h. So then I would like to sketch the orbit. So suppose that this is satellite's orbits, and this is the S's orbit. So this is the center of the S. Here we have radius of the S, R subscript of E, and here we have height of the parking orbit. Suppose that the satellite with mass M is here, and also the S, this is the point where we have the mass of the S. So this is all about the S's surface. Say S's surface, okay, because it's very important, S's surface. And then this is parking orbit, so above the S's surface, parking orbit, and the height is H. So how can we get the height? How can we determine exactly weight that's required to place, or where we can find the parking orbit? So our main objective, we have derived a formula which will help us to know exactly, because this height for the geostationary satellites is known. It's not variable like in some other cases when I was teaching about the satellite motion. Okay, so the second step now, we need to recall a formula that I taught you in period 7, in period 5, or in lecture or session of period 5. Then we have to recall, we derived at the formula of the period. Recall the formula of 40 of determining the period of the satellite. So the period of the satellite at height H. So I told you that we say that the period will be equal to 2 pi, and then you have radius of the S, then you have square root of what? Summations of radius of the S plus the height cube of what? Over acceleration due to the gravity G. Right? So our main goals, we want to make this a subject. So we go for the steady state. The steady state, we say that make H the subject. Right? Make H the subject from this formula. So to make H the subject, you have to square both sides. So you have T square, then here we have 4 pi, then you have radius of the S, but we have to square the whole term, and then you have square root of what? Radius of the S plus the height H. This is cubic of what? Over G. So we have also to square this term. So when we square, so remember that this, I use the subscript of S to say this is the period of the satellite. So we say that the square of the period of the satellite will be equal to 4 pi square, radius of the S square, and then here we have radius of the S plus the height H cubic over acceleration gravity G. Right? So then our intentions, we want to make this the subject. So in order to make it the subject, we have to cross a multiplication. So when you cross the multiplications, we find that on this side we have 4 pi square, radius of the S plus H cubic is equal to what? Is equal to the square of the period of the satellites times acceleration due to the gravity times radius of the S, or square of the radius of the S. So then we have divide by 4 pi square to both sides, 4 pi square like this, and then you have what? The radius of the S plus H cubic is equal to what? Is equal to the square of the period of the satellite, acceleration gravity, radius of the S square of 4 pi square. So then to get this one, remember to get RE plus H power 1, we have to find the cube root of 40 of left hand side, and so the first state, we say that apply cube root to both sides of the formula that we are deriving. So it means that we have to apply the cube root to the radius of the S plus the height H cubic and then you have to apply the cube root. Okay, you have to apply the cube root, then square of the period, and then acceleration gravity, radius of the s square, divided by 4 pi square. Okay, so if that's the case, we say that we have radius of the s plus h, and then we have what? The cube root of what? The cube root of square of the period of the satellite acceleration gravity, radius of the s square, divided by what? By 4 pi square. So now let us make h the satellite. So this will be equal to the cube root of square of the period of the satellite times acceleration gravity, radius of the s square, and then of what? Over 4 pi square minus radius of the s, like this. Okay, so this is the final formula that will help us to determine the height of the parking orbit. So remember that this is cube root, not the square root. So this is cube root of all of these are constant, because all of these are constant. So then now you may use or you can have a question of using that formula to determine the height of the parking orbit, because it's very important for you to understand the concept. So you might have a question, okay? Use these constants. Use these constants. What are the constants? Acceleration gravity. Acceleration due to gravity is 9.8 meter per second square. Again, we need radius of the s is equal to 6.4 exponent 6 meter. And then we need what? Pi is equal to 3.14. That's all. And then so use those constants to determine or to find, determine what the height of the. Okay, so according to the requirement of the questions, use the constants given: acceleration gravity 9.8 meter per second square, radius of the s 6.4 exponent 6 meter, and pi is equal to 3.14 to determine the height of the parking orbit. So solution, the first step, we have to recall the formula, okay, the formula, and this the formula that I taught you. We derived it together. So in the second step, so this formula is familiar with you, that the cube root of square of the period times acceleration gravity times the square of the radius of the s, then divided by the 4 pi square minus radius of the s. So the second step, we have to remember, or have to, yes, you have to remember, or yes, to remember the period of the geostationary satellites, which are always placed in the parking orbit. So the periods of revolutions of geostationary satellites is a day. So we have to convert 1 day into seconds, because the SI unit of the period is what? Second. So then, we have to take 24 times 60 minutes times 60 seconds. So then the height of the parking orbit, will be the cube root of period square times acceleration gravity times square of the radius of the s over 4 times pi square minus 6.4 exponent 6. So remember that this is second square and this is meter per second square. So per second square cancel with second square, right? And then here we have meter square. So we'll have meter square, meter. So here we have meter times meter square is equal to meter cubic, right? In denominator, we don't have any unit. So the cube root of meter cubic will be meter. So the way you have to do this computation by using your scientific calculator, for example, that if you have function Casio, okay, in case that you have Casio, function 991 ms, like this. So the procedures to find the cube root of this quantity is you have to press number 3, right, on your scientific calculator. So you have to press number 3, right, and then next word you have to press shift and you go to the x cube root, x and then square root, like this. Then you introduce your number. So for that case it is 24 times 60 again, and then you square, and then you multiply with what, with 9.8, you multiply with what, with 6.4 exponent 6 square. So that is all about denominator. So then you get the response. Then you divide with what? We divide with the cube root. So it means 3 shift square root of this one. So the cube root of what? Of 4 times what? Times 3. Or you can use 2 times what? Times 3.14 and then square, right? So then this is the response that you are going to get. So the response will be 7.59002 exponent 7 meter. You subtract it with radius of the S, which is 6.4 exponent 6 meter. So after subtractions, the response will be this one. If you approximate, it will be 3.6 because you approximate in one decimal place, 3.6 exponent 7 meter. This is the height of 40 of the satellite. The height of the parking orbit from the SC surface is 60,000 kilometers, right? So that's all about 30, about the height of the parking orbit or the height of the station. It means that each geostationary satellite, whether it is navigation satellites, whether it is GPS satellites, whether it is communication satellites, it should be placed at this height from the Earth's surface. Bear that in your mind that the physics students, at least that you might not maybe know too much about the satellites, but at least you know the desired height from the Earth's surface. So if this is the case now, join me in the next concept when I'll be teaching about the speed. How can we, means the derivation of the formula of determining the formula that will help us determine the speed of geostationary satellites, right? So join me in the next part. So then I'll teach you how to derive, and then we'll use that formula to determine the speed of the geostationary satellite, which is 3.1 kilometer second. Thank you very much. So let us go to the next step.